Could you please give an enormous final day last speaker welcome to Matthew Hole?
Great. Well, thanks very much for that enthusiastic welcome. So, as Chris indicated, this is a field of research that has been around for some time. The early experiments go back to the late 1940s, early 1950s, with the zero-energy toroidal assembly that was pioneered in the UK, through to experiments, the Joint European Torus, which is still the world's largest DT experiment, deuterium-tritium fusion experiment, in Oxfordshire, through to the ITER project, which is now under construction, which will be the world's, well, one of the world's largest and perhaps most expensive experiments, but it has a very strong motivation behind it. So what I want to do in this lecture is talk about what is fusion, what does it offer, what is the science of fusion, and where is it going in terms of international research. So fusion, as you may know, is the process that powers the sun and the stars. So fusion in the sun, for example, combines proton-proton cycle primarily to produce helium, but the reaction that we want to exploit is a deuterium-tritium reaction, heavier isotopes of hydrogen. But the idea... Yep. Ah, all right, yeah, good point. I'm in the wrong location. Okay. Yeah, awesome, no worries. Fine. So the idea is that it can provide essentially limitless fuel available all over the world because its fuel source are primarily isotopes of hydrogen, which is the most abundant element in the universe. It has no greenhouse gases. It's intrinsically safe. It doesn't produce long-lived radioactive waste. It does produce short-term radioactive waste, but it's at the scale of the order of 100 years, not 10,000 years. And it's amenable to large-scale energy production. So it's a replacement to coal on a very long time scale. That's the attraction. So as I said, it's a combination of deuterium and tritium. So deuterium is a hydrogen atom with one extra neutron. Tritium is a hydrogen atom with two extra neutrons. And if you combine those together, and if you bring them together sufficiently close so that they overcome the Coulomb repulsion, because they're both positively charged, they don't want to be together, such that the strong nuclear force takes over, they combine together to produce helium and an energetic neutron. And the power gain for this is a factor of 450 to 1. So this was co-discovered by an Australian, Sir Mark Oliphant, together with Lord Rutherford, in Cavendish laboratories in 1932. And if you compare the energy released per reaction of fusion, fission, and coal, so this is in units of electron volts, so 1 electron volt is the charge of an electron moved by 1 metre in an electric field, is 1.6 by 10 to the minus 19 joules. If you compare the fusion reactions, I'm focusing on the DT fusion reaction. There are the DD fusion reactions as well, which can also be initiated. They have slightly lower energy yield. But if you compare this number and the fission number to coal, it's like orders of millions. It's enormous by comparison to this. So the energy density of nuclear processes is significantly higher, order of millions greater than that of coal. That's the reason why it's appropriate for large-scale energy generation in an energy-dense format. If you compare the energy yield per unit mass of fusion to fission, this has a lot more energy in its decomposition, but if you look at the energy per mass, this is 235, this is still 4 times more energy per unit mass than fission. But both are staggeringly larger by comparison to coal. So the big idea is that it uses small amounts of resource for large-scale energy production. And if you look at the amount of lithium in my laptop battery, plus the amount of deuterium in half a bath of water, this would be enough to power an average person for 30 years. So it really is large-scale energy production at very low resource cost. Where do I get the resources from? Well, as I said, hydrogen is by far, nearly all the universe, visible universe, is hydrogen. And if you look at the abundance of the elements, they're all quoted relative to the concentration of hydrogen. So for every 6,000 hydrogen atoms, there's 1 deuterium, And for every 10 to the 17 hydrogen atoms, there's one tritium atom. So this is rare. And the reason why it's rare is because it has a half-life of 12.5 years. So it's radioactive. Consequently, I need to manufacture it, and I can manufacture it by activating lithium. So what I do is I fire a neutron at a lithium target, and that decomposes into a helium and a tritium ion, and the tritium is what I use to fuel the power source. If you look at then what is the fuel supply of lithium, in about 10 to the 6 hydrogen atoms is one lithium, so lithium is, I think, about the third or fourth most common element, metallic element in the Earth's crust. And in the solar system, it's significantly more abundant. So then if you look at the US Department of Energy, energy usage, this is an old figure. Even if you were to double this figure, it doesn't make much difference. The energy usage for the planet is about 13.5 terawatts. The estimated Earth reserves, you're talking 6 by 10 to the 8 terawatt years of DT. You're talking tens of millions of years of years of supply of deuterium, tritium, and an even more ridiculous number in terms of deuterium-tritium cycle. So it really is a very long-term solution to the energy problem. As I said, though, in order to initiate fusion, you've got two positively charged ions. They have to overcome their electrostatic repulsion in order for the strong nuclear force to take over. So how do you do that? Well, you can do that by a number of different techniques. You can do that by particle acceleration. You can use a linear accelerator. You can even do it on a relatively small scale on a crystal block, about so big or so. Indeed, the University of Sydney, my colleague, Associate Professor Joe Kashan, has a number of experiments in which he generates large amounts of neutrons. But they don't translate to energy production, because to translate to energy production, I have to have significantly more power out than I put into the machine. So they're great as a neutron source, but they don't translate to power. If I want to translate it to power, I need to use a different approach. One approach that is being used is inertial compression. So in inertial compression, you fire a whole bunch of lasers to a target. And the idea is that if you uniformly illuminate the target, you can heat the target by both direct radiation and indirect drive, and cause a shock wave to be launched which compresses the target to a very small point and initiates fusion. This technology, inertial compression, is somewhat more controversial, however, because the primary point of it is a weapon program. In the US, the National Ignition Facility is funded by about 90% by the Nuclear National Security Agency and is designed to continue weapons testing in a comprehensive test ban environment. So this technology, whilst in principle, perhaps it might be able to be used as civilian power generation, it has a secondary driver, and most of its funding source comes from that secondary driver. There's a catalytic process, muon catalysis. This is real. You can generate muons from a nuclear accelerator, and these lower the potential energy barrier in order to initiate fusion reaction. Please go ahead. The energy required, yes. So what it does is that it lowers the potential energy barrier to initiate the reaction. So if you think of it like a potential hump and a well, in order to get over the potential hump, I need a certain amount of energy. But the deep trough point, the difference between the initial and final state, is still net energy yield. What a catalytic converter does is it reduces that potential barrier to initiate reaction. So that would be ideal if you could make that work, because rather than having to heat rather than having to overcome this very high potential barrier due to electrostatic repulsion, I could do this at much lower energy cost initially. The problem is that these muons have an extremely short half-life, and so I'm not able to effectively utilize this to produce power. The approach that we're going to exploit or look at today is confinement, and there are different ways of confining a plasma. The sun, nature does this very effectively, but that's because it can harness gravity. If I have the object sufficiently big, there's enough gravitational pull to lift the fuel ions, to temperatures which are sufficient for fusion reaction to be sustained. I could use an electrostatic gridded ion accelerator, which is whereby I have a series of meshes which might accelerate ions to a target. This can also generate fusion. At the present time, this is not something that is believed will be able to translate to a power plant. However, that doesn't stop companies like Lockheed Martin in the US from trying and making a big song and dance about it. In that case, I think Lockheed Martin was probably interested in funding as opposed to real science. But, you know, when you get to big science, there are interesting politics that drive big science in addition to interesting science. And the topic that I want to talk about is toroidal magnetic confinement, which is probably the most developed pathway to realizing fusion. So as I said, you have to lift the hydrogen ions, or the hydrogen ions, sufficiently close to allow the electrostatic Coulomb barrier to be overcome. So here's a plot which looks at what's called the collision cross-section, which is the probability of reaction as a function of ion temperature of the constituent components. And so if I look at, for the DT, the deuterium, helium, and the DD reactions, these peak, or at least for the DT reaction, at around about 100 million degrees centigrade. So that's the condition that I need to exploit. If I want to maximize the reaction probability, I need to have my constituent plasma extremely hot. The density is going to be proportional to the energy yield. If I have a higher density, I'm going to produce more power. And I have to maximize this energy confinement time. What's the energy confinement time? Well, if I boil a jug and let it cool down, the energy confinement time is an insulation parameter. It's the amount of time that it takes for that jug of hot water to lose energy to the surroundings. If I combine these together into a power balance calculation, I can produce what's known as this ignition criteria, which is where this triple product of those three things has to be bigger than a threshold for the fusion power to be greater than the heat loss. And under those extreme conditions, matter exists in a plasma state. So what's a plasma state? Well, plasma is an ionized gas. If I look at all the atoms in this room, all of the atoms, almost exclusively, will have electrons bound to them. And if I apply a magnetic field in this room, nothing will happen unless you have a pacemaker, in which case you're in trouble, or some items of metallic origin, which might be flung to the wall. However, if I strip the electrons off the ions, so that I have charged ions and charged electrons, and apply a magnetic field, what will start to happen is the particles will start gyrating around the field lines. They'll be confined to the magnetic field lines. And the stronger I make that magnetic field, the more tightly they will be bound to the magnetic field line. So nearly all of the visible universe is in the plasma state. If you look up at the night sky, what you principally see is line emission from electrons that are in excited states de-exciting, but what you're seeing is line emission from a plasma. And so this process, whilst it's not necessarily, the state is not common on Earth, except for lightning and the aurora, for example, it is nonetheless extremely common in the universe, and it's the process that powers the sun and the stars. So let's look at toroidal magnetic confinement. So what I want to do in this topic is that I want to be able to confine the ions and electrons along field lines. And the reason why I want to do that is if I try and lift a gas to 100 million degrees centigrade, there's no material that's going to be able to withstand that enormous temperature. It's just going to be ablated immediately. So I need to find some way of electromagnetically confining the plasma. I can't control gravity, as I said, so I'm going to do that magnetically. And as I said, the stronger I make the field, the more tightly these ions are bound to the field lines. So the idea is that I put a very strong magnetic field. The alpha, the deuterium, and tritium ions are confined to the field. The neutrons are not charged at all. The neutrons go straight out of the vessel and they heat the wall. If I took a linear machine like this and did that, well, the particles would be confined across the machine, but they wouldn't be confined along it. They'd simply fall out. So the easiest way to try and create a device that's going to confine the plasma is to bend it back in on itself. And the most successful magnetic confinement device is called the tokamak, which is really a Russian acronym for toroidal magnetic chamber. So what are the components of a tokamak? It comprises an immediate metallic vessel, which comprises the plasma or gas that you want to ionize. This thing's not working quite well, so I'm using this at the same time. I apply to that a series of toroidal field coils. So what these do is that I apply a strong current, or a large current, rotating, let me see if I do this correct with my right-hand rule. So I want to do it, a current going in that direction. That produces a strong magnetic field around the machine. So I can see some people using the right-hand rule, so people do know about that. That's great.
Nice to know what he's actually used.
That's true. Then what I do is I apply a central solenoid. What I'm trying to do here is I've got a series of field windings around this, which are going to, these are coils in which the current is spiraling around the center column. And the idea is that that's going to generate a large magnetic field, which is around the outer winding of this transformer. And then by Faraday's law, I'm going to induce a plasma current inside the vessel that's going to be established so as to oppose that established magnetic field. So what happens is that I induce a large current rotating around the machine so as to oppose that induced EMF by the central solenoid. That creates a confining poloidal magnetic field. So poloidal is now the short way around the tokamak. And I add to that some shaping fields that guide the guide the field at the upper and lower midplane of the machine. So the idea of this is that it creates a magnetic bottle. What I've done is I've constructed a combination of a strong field in this direction externally with a field that is in this direction, poloidally, and added some shaping fields so as to create a magnetic bottle. So if I have a tokamak experiment like this, for example, and I don't turn the magnets on, the particles will just diffuse. They won't diffuse outside the box. That's a problem with the simulation. But nonetheless, they will just diffuse. If I turn the magnets on, what will happen is the particles are now confined to the magnetic field lines. But these particles over here, these large ones are the ions, and these smaller ones are the electrons. So what's happening now is that the field, if I look on the left-hand side of this, the field is coming out of the page. The field gradient is this way. So if I go from the edge of this machine to the center, the field increases. Why does it increase? Because there is, if I look at the field is going to be proportional to 1 on this major radius, simply because this is closer to the central axis of the machine. Consequently, the ions, when they rotate, when they undergo this spiraling motion along the field lines, their gyration radius will be smaller on the inboard side relative to the outboard side, and they will drift down the machine. The electrons, which have opposite charge, will experience the same effect, but they'll drift in the opposite direction. So the consequence is that if I just had a machine with a toroidal magnetic field, I would end up with particle separation from ions and electrons, which would produce this electric field, which would make this plasma geometry unstable. The way I get around that is by turn on a plasma current. So if I now turn on a plasma current, the field lines are no longer toroidal. They twist. They twist around the machine. And this means now that the ions and electrons don't experience this charge accumulation at the top and bottom of the machine, and I end up with a confinement configuration which is more or less stable. So what I'm doing here is I'm trying to explain how you end up with a magnetic bottle which confines the plasma. So here's my plasma. This thing, as I mentioned before, this is the magnetic field line. And this magnetic field line, in this case, If I follow this magnetic field line, it will bite its own tail. If I follow it long enough, it will reconnect back into itself. In a perfect tokamak, which is symmetric in this direction, the field lines will lie in flux surfaces. So if I follow this field line, it will always lie on one of these surfaces. Here's a surface, for example, that innermost surface. If I follow that, the field line will always lie on that flux surface. If the field is sufficiently strong, these ions and electrons are bound completely to that field line surface, because the Larmor radius, this gyration radius, is extremely small. These different flux surfaces are then more or less thermally insulated because there's no particle excursion across the machine, and these flux surfaces can then support a pressure gradient. And a tokamak needs to maximize this core pressure because I want to lift the temperature of the machine to 100 million Kelvin. So what I have now is a device that has extremely good thermal insulation. And part of fusion science is really about making a magnetic bottle that has very good thermal insulation. What I want to do is I want to maximize the number of these flux surfaces at a very strong field strength. And by doing this, I create a magnetic bottle. So that's the magnetic configuration. I said now I have to lift the temperature of the device to 100 million Kelvin. Well, how do I do that? I can use a combination of ohmic heating. So ohmic heating is if I drive a current through a wire, the wire will heat up. However, the conductivity in a plasma is proportional to temperature to the power 3/2. So as the temperature gets hotter, the plasma becomes much less resistive. And if you try and pass a current through a wire, you know that the power loss goes like I squared R. So the higher the resistivity, the bigger the power loss in the system. What the problem is that I can't heat the plasma very much because eventually the resistivity becomes so low that I limit the temperature to which I can heat the machine. So I can limit it, in this case, to about 3 keV. So one EV is about 10,000 degree Kelvin. So 3 keV is about, what's that about? It's about 30 million degrees centigrade. I need additional heating. So where am I going to get that? I get that by a combination of electromagnetic waves, which is microwave heating power, effectively, the same thing that you'd use to heat food, and then neutral beam injection. So this I don't really need to explain. This I do. So neutral particle beam injection is a bit like billiard ball physics. In fact, it is billiard ball physics. What you do is you have an ion source, you have a mesh, you accelerate the ions. If I have an ion source going in this direction, it's not going to enter the plasma because the ions are charged. The ions will be deflected outside the plasma because they see this very strong field gradient. Please go ahead. Sorry? So the tokamak, I talk a little bit about that further on. The tokamak itself, this is an evacuated chamber, and it's got a gas inside that you initiate breakdown in the gas to make it a plasma. So when I say initiate breakdown, what that is doing is it's stripping the electrons off the ions. The actual machine itself is metal. The machine, the vessel walls are metallic. The inner surface of this is coated with interesting combinations of either tungsten or carbon or beryllium, and I'll get onto the reasons why we do that a little bit later. But turning back to this again, so if I have a charged particle, it won't enter the plasma because it will be experience this deflection. So what I do is I have a charge exchange gas. So if you have a charge exchange gas, you have a fast ion coming along. It hits a neutral particle, which is very slow. The charge goes from the fast ion to the neutral. The neutral is pushed in one direction, so you end up having a neutral travelling in this direction. And what was the slow thermal particle now becomes a slow ion. So literally, if you take a billiard ball set and fire and shoot the billiard ball, you can transfer the energy of the fast particle, i.e. the billiard ball that you're striking, to the object that you want to hit. That's exactly what happens here, that to drive this into the plasma. Subsequently, what happens is you end up with the same thing happening inside the plasma. The fast neutral collides with a thermally ionized particle, the fast neutral now becomes a fast ion, and the slow ion becomes a slow neutral, and that diffuses outside of the plasma. So this is billiard ball physics, but it's extremely effective in terms of heating. The last is what you actually want to heat the plasma in a sustained context, which is this deuterium-tritium reaction. So the helium ions are confined, they have 3.5 MeV, the neutron is unconfined, but this helium ion will do much of the self-heating of the plasma. So I mentioned this triple product, and this picture is trying to show, as a function of central ion temperature and time, the progress in this fusion triple product over time. And all of these points represent different machines. So forget about the labels, they don't mean much except they describe a different machine. What's important is that it's gone from something which is down to 0.01 in the early 1960s through to a triple product which is approaching this break-even regime. So what's a break-even regime? A break-even regime is where the output power is equal to the auxiliary input heating power. And the experiment that's been able to demonstrate that the highest yield in terms of that power gain is the joint European tokamak in the UK, which is still operational. And that produced a power gain of 0.7 with 16 megawatts of input power. You could ask, well, that was a long time ago. What's happened since then? Well, since then, the machine didn't need to do parameter pushing because it could have gone to a value of Q of 1.5 or so, but it can't go any higher than that. And the reason why is because it wasn't designed to do so. Question?
What's the limit of Bremsstrahlung?
Sorry?
What's the limit of Bremsstrahlung in the diagram?
The limit of Bremsstrahlung is braking radiation. So I don't know whether you covered braking radiation. This region over here is, what this is showing is a reactor-relevant condition. If I go to sufficiently low temperature, but sufficiently high fusion product, I end up with what I'm trying to say is that the plasma is not going to it's not going to be suitable for a reactor environment. I'm going to come back to that question in the next lecture because I know the answer to that, but you're going to put me off track if I go into too much detail now about it. In any event, the machine that's produced this highest configuration is the joint European torus. The next step fusion experiment is to try and go to what's called the burning plasma regime, where the power gain is a factor of 5 or more. So now I put a deuterium and tritium ion into it. This thing has 3.5 MeV. The neutron has 14 MeV. If I look at the ratio of the total power, P heat plus P out, over P heat, it's a factor of 5. And in that instance, what it's saying is that the power out, the input power from heating is equivalent to the auxiliary input power from the plasma from heating. And this is known as the burning regime, where at least half the heating is coming from the fusion alphas, and the overall power gain is greater than a factor of 5. ITER is also designed to explore a controlled ignition regime. What do I mean by ignition? Well, ideally in a power plant, you want to turn off the auxiliary heating altogether. You want it to just burn. It's a bit like trying to light a fire when it's raining. You might have to keep blowing smoke into it or throwing kerosene onto it, for example, in order to make it light. I don't advise doing that. I've tried that. That's a very bad idea, even if it's raining. What you want to do is eventually turn off that auxiliary heating input, which turns it into a power plant. ITER is intended to explore this high Q regime, but only for very limited time. It is intended to explore the Q of greater than 5 regime, more or less continuously. This picture is a bit of a political figure, but the reason why I'm including this here is just to show that this has really made significant progress over time. This is the number of CPU transistors per unit area on a silicon wafer. Okay, this figure's a little bit dated, but the point that you can see is that this has really made quite significant progress. It's comparable or perhaps exceeds Moore's scaling law, depending on when you take the time slice at which you capture this data. Let's go right ahead to the end point, because I'm trying to give you an overview of what a fusion power plant would look like. So to a large degree, the electricity generation part doesn't look substantially different to a coal-fired power station. So in a coal-fired power station, you heat water to create steam. Steam drives a generator, which then drives a turbine and produces electricity. So the central difference is the heat exchanging element in a fusion power plant comes from a DT plasma. And so the heat exchanger in this case, this is looking down on top of the machine, is a blanket, and the blanket in this case is insulating the plasma from, well, it's a mechanical insulator if you like, going from the first wall of the plasma, which is of the order of thousands of degrees, down to ambient temperature, and you're pulling heat out of the wall to drive your steam turbine. There are some aspects of this that are different. The fuel supply is obviously different. There is a reprocessing, if you like, or processing of isotopes that come out of the machine. So in this case, you're trying to extract helium from the machine because helium is the ash. I'll come to that in a second. The helium is the ash of the machine. You don't want it. What you do want to do is you need to generate tritium because tritium is one of the fuel supplies, and I do that by activating lithium. So I have a component of this, which is a tritium breeding module, which is supplying tritium to the machine. So what I'm trying to do is give you an overview of the point of that the actual electricity generation part of this is not significantly different to a coal-fired power station. The heat exchanger and the fuel conditioning part is different. Question? Someone had a question. So the heat is coming from this energetic neutron. As I said, the deuterium-tritium reaction creates an energetic helium ion, which is charged, and that remains inside the machine, more or less. It can diffuse out of the machine, but it remains more or less confined. The neutron has no charge. It goes straight out of the plasma and slams into the wall of the machine. And so when it slams into the wall of the machine, it heats it. It's very energetic. So the heat is coming entirely, almost entirely, from neutron irradiation onto the wall of the machine. That's what's heating it. This is an old slide, but I only include this to give you an idea of... People do lots of economic modelling of various different things, and people have done this type of economic modelling for fusion. And the only reason why I put this up is to say that, look, there are scenarios under which fusion is believed to be competitive to other technologies. So often, ignore solar PV for a second, I'll come back to that in a second. Often you can divide, projections for power to the grid are divided between internal costs, which are the costs of construction, fueling, operating and disposing of power stations. And in that context, fusion is comparable to tidal. At least this is an old study, and that's why I said ignore solar PV. And external costs, which are the estimated impact costs to the environment, public and worker health. And in this case, fusion is comparable to wind. So the point is that studies have been done that suggest that fusion may be competitive. The reason why I said ignore solar PV is because, well, this is over 10 years old, and solar PV has made significant advances in internal costs, and that is now much, much lower than the error bar, than the measurements suggest. Question?
So with this progression of fusion technology, does that mean it will one day become preferable over fission?
Well, the idea is that I haven't compared it to fission here. So fission is over there somewhere. It's probably comparable in the long term, perhaps, to fission. There's a huge amount of uncertainties in this. Chris mentioned uncertainties in the very beginning. This is a research program, and it's a question of to do these things sensibly, you can only make a real economic comparison based on mature technologies. So if one projects 50 years into the future and making assumptions that we believe are appropriate based on current understanding, it's possible that fusion will be comparable to tidal and fission. Is it going to be less than fission? I have no idea. Only time will tell. As I said, this is a research program. But what I wanted to indicate is that people have done such studies, and there is at least some plausible economic basis for that science investment. That's one of the reasons why it's invested in. I mentioned radioactive waste. So fusion itself, the product of reaction is not radioactive. The neutron is stable. The helium ion is just a helium ion. But the neutron is very fast. And so when the neutron impacts into the first wall, it can activate it. And the consequence of this is that whilst it doesn't produce direct radioactive waste, it produces indirect waste because the whole facility, or the first wall of the machine in particular, becomes activated over time. However, one has to ask the question, well, how activated? So if you look at a fission reactor and you shut it down, this is the decay curve in curies per watt of a fission reactor years after shutdown. And it's the question of how much, I'll get to your question in a second, how much more or less radioactive is a fusion power plant? So if you look at existing reduced activation ferritic steels, after around about 100 years or so, it is more than 3,000 times less radioactive than the waste from a fission power plant. And if you used advanced vanadium alloys, it's almost a factor of 1,000,000 times less after 30 years of shutdown. So there are studies that have shown that if you turn a power plant off, you can and wait for 100 years, the level of radioactivity of the first wall itself reduces to background levels. Whereas if you turn off a fission light water reactor and look at the fuel, the spent fuel, it's taking thousands, if not tens of thousands of years to reach background levels. So both the volume of waste and the length time, the scale time in which you have to wait for the fuel, or the fuel, in this case not the fuel, but the facility itself to become approach background levels is significantly less than that of fission. And that's one of the attractions of fusion. Question?
You said that the reaction produces helium. How much helium would be produced and what would you do with the helium that was produced?
So the amount of, well, I mean, the first comment to make is the amount of deuterium and tritium inside the machine is very small. It's like kilograms, because this is a very high energy dense, density reaction. The helium that's extracted, well, the idea is that you extract it using some separation technology, a centrifuge, for example, and then you can do whatever you like with it. You can sell it. I don't know how much you can buy helium for. The point is that the first point to note is that we're dealing with small quantities of fuel. So the extracted helium is still going to be small quantities of fuel. It's going to be like kilograms. So we're not talking about a large amount of material. What you can do with it then, well, I don't know, sell it or something. But the waste issue is just not an issue for fusion power in terms of the direct products of reaction. The indirect products of reaction, the first wall, is a problem, but it can be addressed. So, okay, I mentioned that fusion's made this significant progress. In order to reach this burning plasma regime, I need to go to a much bigger experiment. And there's reasons for this that I'll explain in a few minutes. But the next big experiment is this International Thermonuclear Experimental Reactor being built now in Cadarache in the south of France. Here's a person by scale. It won't produce power, but it will have a fusion power gain of between 5 and 10 in steady state, approaching 30 for short duration. The power out is about 500 megawatts. It's a consortium of 7 nations and alliances, and it has various collaboration agreements with a number of other institutions. And interestingly, if you look at its construction plus 10-year operation costs, it's of the order of 20 billion. You know, it may end up being double that because big science projects, the Large Hadron Collider is another example, end up going over budget. And the reason why they end up going over budget is because it's a research project. You don't know, you haven't done this before. You've got really no idea how much this is going to cost. You can only do your best estimate at the time. I'll come back to that in a minute. But the point is that it is fiscally the world's largest single science experiment. The International Space Station is more expensive, like it's $100 billion. But if I ask the question, do I need to build an International Space Station to do an experiment in space? No, I don't need to do that. The International Space Station is like a building. It comprises experiments. If I want to build a machine to explore a burning plasma environment, I need to build a machine of the scale of ITER. ITER is a physics experiment. The International Space Station is not. It's a building. It's a building that happens to be in space. What are the program objectives of ITER? Well, it's to demonstrate feasibility of fusion energy for peaceful purposes. It's to produce and study a plasma dominated by this alpha particle self-heating. There's a lot of grand challenge burning plasma science, which is of interest to me as a physicist. And what happens when you start having this significant energy, a significant amount of fusion alpha heating, is that the plasma will self-organize into a different state than that we have at present, and you'll end up with a distribution function that may be far from Maxwellian. So much of the conventional physics understanding, which is based on lower temperature plasmas, will be challenged in this environment, and that's a physics challenge. There's another aspect of ITER which is extremely important, is that it's also a technology integration experiment. I'll get to your question in a second. So what it's designed to do is to demonstrate this integrated operation of these different technologies en route to a power plant, and it's also designed to investigate this crucial materials issue. So in fusion you have this very large neutron flux that's coming out of the machine, and if you look at the neutron flux loading, it's greater than 0.5 megawatts per square metre. ITER, well, will be able to handle this, but when you go through to a demonstration power plant, there are no materials that can withstand that neutron flux. So there is a real materials question about how you develop materials that handle that very high neutron flux, and there's also a question about how you develop materials that handle a very high thermal flux, particularly in a region known as the divertor, which I'll talk about in a second. So there's two aspects of this. There's a technology aspect, which is of interest to me as a physicist, and there's a technology angle, and particularly a material science angle, which is developing high temperature materials to handle the environment from hell. That's a great quote that is sometimes used to sell a grant application. So here's ITER in detail. As I said, the minor radius, well, the fusion power is 500 megawatts. This minor radius is the radius from the center of the machine to the edge, or the center of the plasma to the edge. This radius is 6 meters from the machine axis to the center of the plasma. And if you look at then the total volume of plasma, it's approaching that of an Olympic swimming pool. It's big. And there's your standard candle person down below. The toroidal field strength at 6.2 meters is 5.3 Tesla. So the only way you can make a field strength of 5.3 Tesla is by using superconducting magnets. So that means you have these field coils around it, which are cooled down to liquid helium temperatures at 4 Kelvin, going from a temperature gradient from 4 Kelvin to 100 million degrees in the core of the machine. A staggering temperature gradient. And at the field conductor itself, the field is not 5 Tesla, it's 12 Tesla. The auxiliary heating and current drive is 73 megawatts. So running this at 50 megawatts of heating produces a power gain of 10. And it's around the machine, I mentioned this toroidal plasma current, it's got 15 mega amps of current. That's 300 lightning bolts flying around the machine in the core of it. It's a very high energy density experiment. So let's ask the question, what do those plasma performance parameters mean? So the present devices I mentioned have a power gain of less than 1. ITER will explore Q greater than 10 in controlled ignition for short duration, Q greater than 30. The central ion temperature is about 10 to 20 keV, about 100 million degrees, which is about 10 times hotter than the core of the sun. The energy confinement time, which is the time that it takes for the object to cool down, is a couple of seconds. The plasma pulse duration is like 1,000 seconds, so it's effectively the experiment lifetime is more or less steady state relative to the energy confinement time. And this thing, the energy confinement time, is set by turbulence and magnetic geometry. This is where most of the plasma physics come in, is trying to maximize that energy confinement time, maximize the insulation parameter. And the density, which we expect is around about 1 by 10 to the 20, and this is determined largely by the ignition condition criterion. There are some stability limits that will apply to the density as well. But if you look at this number, it's around about 10 to the minus 6 of atmospheric particle density. So Chris mentioned early on Fermi calculations. Let's do a quick Fermi calculation to work out what is the pressure inside the machine. So the pressure inside the machine, that's 10 to the minus 6 of atmospheric particle density, but the temperature is like 100 million Kelvin. So these more or less cancel. And if I look at the numbers, I end up with a pressure which is around about atmospheric pressure. So in terms of the actual force that's exerted in the machine, you're talking about a couple of atmospheres, but the temperature is 100 million Kelvin. The density is a factor of 10 to the 6 times less. There's another part of this which I want to talk about, which is this confinement energy scaling, tau E. And the first comment to note is that this plasma energy and particle transport is largely driven by turbulence, or set by turbulence. So it's found that, that depending on what regime you operate the plasma in, you can either have this low confinement mode, which is where this tau E condition follows this low threshold scaling. So in this case, this is in seconds, it's about 0.5 seconds or so. Or it can bifurcate into this high confinement mode, where tau E is a factor of 2 or more higher. And that's important because in order to make fusion power work, you can establish that I need to be in this high confinement mode. And what's the difference? Well, okay, now if you look at the plasma temperature for this low confinement mode, the low confinement mode, the core temperature profile doesn't look substantially different to the high temperature, the high confinement mode throughout most of the plasma, except in the edge. And the difference is that in the high confinement mode, I end up with this temperature pedestal, or cliff, if you like, right at the edge of the machine. And so what happens is that the whole temperature profile is lifted by a certain edge pedestal jump pressure at the edge of the machine, and that improves tau E. It also means that I have a strong plasma temperature and density gradient at the edge of the machine that can drive certain types of wave modes called edge localized modes, which are a problem. But hey, life's a trade-off. In order to make this tau E sufficiently large so as to exploit fusion power, I need to be in this H mode confinement. It also produces these edge localized modes. I have to live with them. So the question is, okay, what now sets this tau E quantity? Well, you know, when physicists don't really understand something, they do something which is kind of evil. They say, well, I don't understand what the dependence of an object is. I'll just twiddle all the knobs and see how it fits to an empirical scaling. Or I use dimensional analysis. Now, it's kind of evil because it says, well, I don't know anything about the physics of this. I'm just going to try and predict it from experiment. And that's exactly what physicists did, is that they varied all these knobs in existing experiments, varied the plasma current, the field strength, the heating power, the machine size, and so forth, and they worked out how does it vary with plasma current and machine scaling. And the immediate thing to note is that it varies with the square of the machine size, so bigger is much better, and it also varies linearly with plasma current. I want a big plasma current. So if I then fit all of this data, this predicted scaling, to this scaling law, I can see that most of these experiments fit on this scaling law. So much of the science basis for ITER is based on the prediction, or on the observation, that I can fit all this scaling to a common line, or a common functional form for tau E, and if I work out where ITER will fit, well, ITER will lie up here. Those who might be more astute will note, well, that's interesting. Two things are interesting. This is a log-log scale. That's true, it is a log-log scale. You can commit all manner of sins when you plot something in a log-log scale because it buries any detailed dependence. And the other point to note is that this is going by a factor of tau E of 1 up to a factor of tau E of about 5 or so. There's quite a big jump in parameter space here. That's also true. So there are some of us who argued that, well, maybe we should have built a machine which is a half-level increment to ITER to begin with, rather than going a full jump. But, you know, that's a political decision as well. So there's uncertainties here. We don't know whether or not that tau E energy confinement time scaling will work, but we believe that it will. The other aspects that determine the size of the machine and are its stability considerations. So I mentioned that the field undergoes this helical pitch around the machine. If I look at that helical pitch, which is the toroidal per poloidal transit of the field line, so if I follow the field line, it's the number of times it goes around in the short direction relative to the number of times it goes in the toroidal direction. That field pitch is proportional to 1 over the current, and it changes across the plasma. Generally, the higher the Q value of this machine is, the more stable it is. That's why Q was initially referred to as some sort of safety factor. The higher the Q, the more stable the machine. And the other thing that determines it are the materials limits, so the radial build of the machine. So I mentioned you have to drive a solenoid current to produce this field wire, this current around the machine, so as to induce toroidal current. If you look at the superconducting, central column and you apply a field of less than 10 Tesla for that, that implies a certain radial width that the ohmic coil has to be. If I look at the shield, I said that the plasma has to be shielded from the thermal insulation. There's a certain amount of distance that existing materials will withstand in terms of neutron flux loading, and that limits the radial width of the machine, at least on the inboard side, together with the toroidal field coil, because I have to put the toroidal field coil winding back through the centre of the machine. So if I do all of these things, it determines the radial width that I can make the machine. Now if I fold all of these things together, the tau scaling, the design objectives, the magnetic stability, and the materials limits, I produce an ITER class machine. So the point is, if I want to make a fusion power experiment to explore the burning plasma regime, I am forced to build a machine the scale of ITER. I have no choice. That's what the physics and materials science dictates. There's a very good reason why ITER is the scale it is. So what are the big plasma challenges? Well, there's a bunch of different things. There's to produce and study a plasma dominated by alpha heating. There's new instabilities in these burning plasmas. So when I have these fast ions generated from the machine, as they slow down, I'll talk about this more in the next lecture, they can short-circuit the heating of the thermal plasma, and they can drive what some people refer to as thermonuclear ringtones, instabilities that can limit the performance of the machine. That's a fascinating piece of physics. There are these edge localized modes. I mentioned that the pedestal is this increase in the temperature and density at the edge of the machine. A consequence of doing that is that the field lines can become unstable right at the edge of the machine. So this shows field lines erupting through the edge of the machine in the megaamp spherical tokamak in the UK. So there's a lot of, people have often drawn the analogies between this and solar flares, which are solar prominences that erupt outside the edge of the sun. This is the same type of physics that's occurring in this machine. There's a series of disruption mitigation technologies that need to be developed. Basically a giant airbag for ITER. So if ITER becomes unstable, if the plasma becomes unstable, it poses no risk to worker or anybody else's health. There's just an issue that it has a large amount of stored energy and it can damage the vessel. So what I need to do, one technology approach to this is to develop a massive gas puff injection, which is like a giant airbag for the plasma. It fires a huge amount of gas very, very quickly into the plasma, so as to mean that the plasma, the forces, particularly the J cross B forces, are dissipated in heating the external gas, as opposed to being dissipated by ripping a field limb off the machine. There's whole sorts of real-time mode control and identification and measurement of what's called integrated modelling of plasmas under these extreme conditions. So there's a whole bunch of plasma physics challenges. There's some material choices for ITER which have been chosen now because the machine's under construction, and they're chosen for particularly good reasons. So I think the carbon composite fibre tile has actually been replaced now by tungsten, but the point is that I need, in this diverger region, if I follow the field lines internal to the machine, as I showed, the field line will follow that flux surface everywhere. Right at the edge of the machine, however, if I follow the field line across here, it will approach the edge of the machine, and at this point here, it will strike the wall. So the consequence, if I have a particle which is gyrating around this field line just outside this closed separatrix region, it will slam into the diverter on these red regions. So these red regions need to be able to handle an extremely high heat flux loading to withstand the peak target power is of the order of 10 megawatts per squared metre. And so the conventional choice was using carbon. I think that may have been changed now to tungsten. Elsewhere, the machine is clad in tungsten, and the reason why you would choose this is because it has low sputtering and to limit tritium co-deposition. So the problem with carbon is that it has a tritium co-deposition problem. It absorbs tritium, and then you have tritium dust accumulating inside the machine, which is a radiological hazard. And elsewhere around the machine, you'll have this beryllium first wall, and the reason why you would choose beryllium is because it's low atomic mass, and so it has a low plasma impurity limit, but it can only withstand a relatively low heat flux. So why do I care that it's low Z? Well, it's because if I have a plasma and I try and put gas puff into the machine with a high Z, the bigger the atomic wave number, what will happen is that most of the energy will go into stripping off electrons off the atom. So one way to cool the plasma very quickly is to put a very high atomic mass gas into the machine. Because what it means is most of the energy goes into ionizing the gas. If I want to be able to put in a gas for which there is very low ionization potential, I choose a low atomic mass number. Beryllium, however, is carcinogenic, so it creates a safety problem. Now if I turn to the materials challenges beyond ITER, and in particular what I want to focus on is the neutron flux. So I mentioned the neutron flux, which is the neutrons are not confined, they exit the machine. For the existing experiments, this neutron flux limit is tiny. So dPa is displacements per atom. So this is the number of times an atom on the first wall will be displaced by a neutron event. So in the case of an existing machine, it's tiny. In the case of ITER, every single atom in the first wall will be displaced by a neutron event over the lifetime of the experiment. In the case of a demonstration power plant, every single atom in the first wall will be displaced by 100 neutron events. That's a staggering amount of damage. The material has to be able to anneal or recover from this extremely high neutron damage over the lifetime of the power plant. And that creates a real materials challenge. It's also a motivation for a parallel irradiation facility that I'm not going to talk about. There are some other unexpected big physics challenges. So 90% of the ITER components will be supplied by in-kind contribution through the domestic agencies. So they've split up all the pieces of ITER, and now they're being contributed by various different nations and alliances. This creates a problem because, let's suppose I have 24 field coils around the plasma. Actually, there are 18 of them, but they're being contributed by both the European Union and Japan. So they're being built in different places. Now, the important point is that each of these toroidal field segments has to be identical. And if they're not identical, the machine won't fit together. So I have an immediate quality compliance issue. I can't just reorder this because each toroidal sector is like $800 million. This is not a small amount of money. So there's an immediate quality compliance. I have to make sure at the time the device is built that each of the pieces follows an strict quality compliance, otherwise the machine will not fit together. That creates a problem. I mean, if you were to try and build this thing from scratch, you would not choose this model of distribution of various different components. You'd do all of the components in the same place, where you had quality control over every single piece.
Matthew, just for a sense of scale, back on that picture.
Let me go back, hang on.
How big is that?
Well, I mean, don't know there is a standard person down here for scale. They're somewhat obscured by that red arrow there. So each of these toroidal field coils, this is like about, the whole device is about 60 metres tall. So this piece here is about, well, its major radius is 6 metres. So in this direction, it's like 20 metres in that direction, by about 12 metres in that direction.
It's like a good size sort of 6 to 8 story building.
It's a 6 to 8 story building, and each of these pieces, as I said, have to be they have to be constructed with an incredibly narrow tolerance. Otherwise, each of those pieces will not fit together. There are also some other unexpected big challenges, one of which is design finalisation and cost. As I said, when you build a new science experiment, it's very rare that the design is finalised at the point of commencement. And the reason why is because, well, nothing's ever really designed properly until the thing's actually built. That's the standard of any big infrastructure piece, even building this building, for example. Chris was telling me there were some problems with the lights to begin with. So it's often the case that, you know, the cost of something is never really known until you build it. And the design is never known until finally you come around building it either. That does create a problem because each of the different partners have different diverse cultures and management approaches amongst members. As a scientist, you never really think of this stuff, but it really does make a difference because each of those members have promised different things to their governments. The Koreans in particular promised their government that they would comply with a certain timeline in which this first plasma was around about 2018. And they said, do that or we won't give you more money. Now that creates a real pressure-driven problem for some of the different funding partners. The other comment is that there's a broad range of expectations. Some are doing this because they want fusion power on a timescale of 10 years. Some are doing this because they want fusion power on the timescale of decades. It makes a real big difference. And the other comment is that there are different cultures amongst this. The approach of management in the West is very different to the approach of management in Japanese or Korean societies, where it's very much top-down driven by management. In the West, if you say something, if something's not right, you just say it. You don't really care about line management structure. You just say what you think. But in Japan or Korea, you would never do that. So bringing different diverse cultures like that into a truly integrated experiment is problematic. This talks about, nonetheless, ITER is being built. Here's a picture of ITER construction in St. Paul-les-Durance in the south of France. Let's see if this advancer works. Doesn't really work very well. Here's the PF coil winding building up on the top left. Is this advance going to work automatically? No. The cryostat workshop, which is being built by India. There's a big 400 kilovolt substation over here to provide power to the site. There's a building over there, the ITER headquarters. The tokamak complex itself is over here, and that ring there that you can see will be where the machine sits. This is the tokamak building and assembly pit. Curiously, the site of Cadarache is geologically active, so it's subject to earthquakes, which is kind of a strange place to put a big nuclear facility. But nonetheless, that was a political decision. And the consequence is that it has to sit on seismic absorbers. So the whole facility fits on these giant rubber columns sitting around the machine to try and stop and absorb earthquakes, seismic movement, which might happen once in 100 years or so. This facility behind it is the assembly building, the toroidal. I've just pointed the laser. I hope I didn't blind someone just then. That's the assembly building for the machine, which is currently being constructed. There's this colloidal field coil winding facility. Some of the components are too large to be transported by road, and some of the big colloidal field coils, particularly the ones that go all the way around the tokamak, will need to be transported, will need to be constructed on site. There's this cryostat workshop. As I said, the whole thing needs to be cooled down to liquid helium temperatures, so it needs a giant refrigeration unit to be able to cool it. That's been constructed by India. There are nearly 4 billion worth of euros of contracts already engaged in construction on site. And there are 7 billion euros worth of contracts engaged in components and systems manufacturing worldwide. The other interesting aspect about ITER is that it's situated 100 kilometres inland up a mountainside, which is also a kind of funny thing to do if you want to build a large piece of infrastructure, but hey, that was a consequence of political decisions made at the French government level. And the consequence is that they had to put in this giant road network, road and heavy transport network to be able to bring components from the port through to the cataract site itself. And here are some big deliveries that have been started. They need to shut off the roads and transport these things at 3 a.m. in the morning or something like that to mean that they don't have massive disruption to local industry. They've installed some of the first large-scale components. Here's a 400 kilovolt main transformer being supplied. It's actually an in-kind contribution from the US, but being supplied by India. And indeed, first plasmas have already arrived. I mentioned a natural example of plasma is a lightning bolt. This was taken very recently, and interestingly, there was someone actually in that tower at the time. But the tower and the operating crane is like a giant Faraday cage. So they're protected, but gee, they got a hell of a fright. Because when you put up this large electrical towers or large conducting towers, it's an obvious lightning conductor, and lightning is striking the site. So what I hope to have done in the first lecture is at least introduced fusion power and toroidal magnetic confinement, talked about the next step project ITER, talked about its physics and materials challenges, the machine scaling. There is a very good physics and engineering reason why the machine is the size it is. I've talked a little bit about the completion deadline. I had a figure earlier that talked about the timeline to first plasmas. The timeline is currently 2020. The timeline for a demonstration power plant, I guess I didn't talk about that, but it's of the order of 2030, 2035. It depends upon the major partners on what timescale they want to deliver it to, which might provide power to the grid perhaps by 2050. It's a long time. But then again, if you want to build a coal-fired power station of 1 gigawatt, it's going to take you 10, 15 years to build it. So anything in a big energy space takes time. This is not a small timescale response. In the next lecture, what I want to talk about is more of the science of magnetic confinement and plasma physics, and introduce the stellarator. I was in Germany last week, and they had the first they have a new €1 billion experiment, a stellarator, which they first turned the field strength up to full field. And this is a picture of magnetic field lines from electron beam gun, which is one electron beam gun, but it's following the field line around it, and you can see excitation of line emission inside the plasma. What I also want to do is talk about some Australian research activity in fusion, and perhaps give you an impression of what, if you were able to realise fusion, what would it mean? That's why I hope to leave you with an impression of what motivates me to the field. So I'll open it up now for questions. I don't know whether or not I've gone to an appropriate timescale. Please go. Do you want to manage questions, or do you want me to answer those?
First of all, how about a bit of a thank you for that?